Imagine we measured the weight and height of a bunch of mice and plotted the data on a graph. Light mice tend to be short, and heavier mice tend to be taller. But after a certain weight, mice don't get any taller, just more obese. Given this data, we would like to predict mouse height given its weight. For example, if you told me your mouse weighed this much, then we might predict that the mouse is this tall. Ideally, we would know the exact mathematical formula that describes the relationship between weight and height. But, in this case, we don't know the formula, so we're going to use two machine learning methods to approximate this relationship. However, I'll leave the true relationship curve in the figure for reference. The first thing we do is split the data into two sets, one for training the machine learning algorithms and one for testing them. The blue dots are the training set, and the green dots are the testing set. Here's just the training set. The first machine learning algorithm that we will use is linear regression, aka least squares. Linear regression fits a straight line to the training set. Note, the straight line doesn't have the flexibility to accurately replicate the arc in the true relationship. No matter how we try to fit the line, it will never curve. Thus, the straight line will never capture the true relationship between weight and height, no matter how well we fit it to the training set. The inability for a machine learning method like linear regression to capture the true relationship is called bias. Because the straight line can't be curved like the true relationship, it has a relatively large amount of bias. Another machine learning method might fit a squiggly line to the training set. The squiggly line is super flexible and hugs the training set along the arc of the true relationship. Because the squiggly line can handle the arc in the true relationship between weight and height, it has very little bias. We can compare how well the straight line and the squiggly line fit the training set by calculating their sums of squares. In other words, we measure the distances from the fit lines to the data, square them, and add them up. Psst! They are squared so that negative distances do not cancel out positive distances. Notice how the squiggly line fits the data so well that the distances between the line and the data are all zero. In the contest to see whether the straight line fits the training set better than the squiggly line wins. But remember, so far we've only calculated the sums of squares for the training set. We also have a testing set. Now let's calculate the sums of squares for the testing set. In the contest to see whether the straight line fits the testing set better than the squiggly line, the straight line wins. Even though the squiggly line did a great job fitting the training set, it did a terrible job fitting the testing set. In machine learning lingo, the difference in fits between datasets is called variance. The squiggly line has low bias since it is flexible and can adapt to the curve in the relationship between weight and height. But the squiggly line has high variability because it results in vastly different sums of squares for different datasets. In other words, it's hard to predict how well the squiggly line will perform with future datasets. It might do well sometimes, and other times it might do terribly. In contrast, the straight line has relatively high bias, since it cannot capture the curve in the relationship between weight and height. But the straight line has relatively low variance, because the sums of squares are very similar for different datasets. In other words, the straight line might only give good predictions and not great predictions, but they will be consistently good predictions. Bam! Oh no! Terminology alert! Because the squiggly line fits the training set really well, but not the testing set, we say that the squiggly line is overfit. In machine learning, the ideal algorithm has low bias and can accurately model the true relationship. And it has low variability by producing consistent predictions across different data sets. This is done by finding the sweet spot between a simple model and a complex model. Oh no, another terminology alert! 3 commonly used methods for finding the sweet spot between simple and complicated models are regularization, boosting, and bagging. The stat quests on a random forest show an example of bagging in action. Imagine that we have this medical data. We've got some clinical measurements like chest pain, good blood circulation, blocked arteries, and weight. And we want to apply a machine learning method to them to predict whether or not someone will develop heart disease. To do this, we could use logistic regression, or k-nearest neighbors, or a random forest, or some other method. There are tons to choose from. How do we decide which one works best with our data? We start by dividing the data into training and testing sets. Note, this would be an excellent opportunity to use cross-validation, and if you're not familiar with that, we'll check out the StatQuest. Then we train all of the methods we're interested in with the training data, and then test each method on the testing set. Now we need to summarize how each method performed on the testing data. One way to do this is by creating a confusion matrix for each method. The rows in a confusion matrix correspond to what the machine learning algorithm predicted, and the columns correspond to the known truth. Since there are only 2 categories to choose from, heart disease or does not have heart disease, then the top left corner contains true positives. These are patients that had heart disease that were correctly identified by the algorithm. The true negatives are in the bottom right-hand corner. These are patients that did not have heart disease that were correctly identified by the algorithm. The bottom left-hand corner contains false negatives. False negatives are when a patient has heart disease, but the algorithm said they didn't. Lastly, the top right-hand corner contains false positives. False positives are patients that do not have heart disease, but the algorithm says they do. For example, when we applied the random forest to the testing data, there were 142 true positives, patients with heart disease that were correctly classified, and 110 true negatives, patients without heart disease that were correctly classified. However, the algorithm misclassified 29 patients that did have heart disease by saying they did not. These are false negatives. And the algorithm misclassified 22 patients that did not have heart disease by saying that they did. These are false positives. The numbers along the diagonal, the green boxes, tell us how many times the samples were correctly classified. The numbers not on the diagonal, the red boxes, are samples that the algorithm messed up. Now we can compare the random forest confusion matrix to the confusion matrix we get when we use k-nearest neighbors. K-nearest neighbors was worse than the random forest at predicting patients with the heart disease, 107 versus 142, and worse at predicting patients without heart disease, 79 versus 110. So if we had to choose between using the random forest and k-nearest neighbors, we would choose the random forest. Bam! Lastly, we can apply logistic regression to the testing dataset and create a confusion matrix. These 2 confusion matrices are very similar and make it hard to choose which machine learning method is a better fit for this data. We'll talk about more sophisticated metrics like sensitivity, specificity, ROC, and AOC that can help us make a decision in the next stat quests. Now that we have the basic confusion matrix figured out, let's look at a more complicated one. Here's a new data set. Now the question is, based on what people think of these movies, Jurassic Park 3, Run for Your Wife, Out Cold spelled with a K, and Howard the Duck, can we use a machine learning method to predict their favorite movie? If the only options for favorite movie were Troll 2, Gore Police, or Cool as Ice, then the confusion matrix would have 3 rows and 3 columns. But just like before, the diagonal, the green boxes, are where the machine learning algorithm did the right thing. And everything else is where the algorithm messed up. In this case, the machine learning algorithm didn't do very well, but can you blame it? These are all terrible movies. Bam. Ultimately, the size of the confusion matrix is determined by the number of things we want to predict. In the first example, we were only trying to predict 2 things, if someone had heart disease or if they didn't. And that gave us a confusion matrix with 2 rows and 2 columns. In the second example, we had 3 things to choose from, and a confusion matrix with 3 rows and 3 columns. If we had 4 things to choose from, we get a confusion matrix with 4 rows and 4 columns. And if we had 40 things to choose from, we get a confusion matrix with 40 rows and 40 columns. Double bam! In summary, a confusion matrix tells you what your machine learning algorithm did right and what it did wrong. This stat quest follows up on the one that describes the confusion matrix, so if you're not already down with that, check out the quest. The first half of this video will explain how to calculate and interpret sensitivity and specificity when you have a confusion matrix with 2 rows and 2 columns. And the second half will show you how to calculate and interpret sensitivity and specificity when you have 3 or more rows and columns. Even if you're already down with the confusion matrix, let's remember that rows correspond to what was predicted, and columns correspond to the known truth. When there are only 2 categories to choose from, in this case, the 2 choices were has heart disease or does not have heart disease, then the top left-hand corner contains the true positives. True positives are patients that had heart disease that were also predicted to have heart disease. True negatives are in the bottom right-hand corner. True negatives are patients that did not have heart disease and were predicted not to have heart disease. The bottom left-hand corner contains the false negatives. False negatives are when a patient has heart disease, but the prediction said they didn't. Lastly, the top right-hand corner contains the false positives. False positives are patients that do not have heart disease, but the prediction says that they do. Once we've filled out the confusion matrix, we can calculate 2 useful metrics, sensitivity and specificity. In this case, sensitivity tells us what percentage of patients with heart disease were correctly identified. Sensitivity is the true positives divided by the sum of the true positives and the false negatives. Specificity tells us what percentage of patients without heart disease were correctly identified. Specificity are the true negatives divided by the sum of the true negatives and the false positives. In the stat quest on the confusion matrix, we applied logistic regression to a testing data set and ended up with this confusion matrix. Let's start by calculating sensitivity for this logistic regression. Here's the formula for sensitivity, and for true positives, we plug in 139. And for false negatives, we plug in 32. When we do the math, we get 0.81. Sensitivity tells us that 81% of the people with heart disease were correctly identified by the logistic regression model. Now let's calculate the specificity. Here's the formula for specificity. And for true negatives, we'll plug in 112. And for false positives, we'll plug in 20. When we do the math, we get 0.85. Specificity tells us that 85% of the people without heart disease were correctly identified by the logistic regression model. Now let's calculate sensitivity and specificity for the random forest model that we used in the confusion matrix stat quest. Here's the confusion matrix. Here's the formula for sensitivity, and when we plug in the numbers, we get 0.83. Here's the formula for specificity, and when we plug in the numbers, we get 0.83 again. Now we can compare the sensitivity and specificity values that we calculated for the logistic regression to the values we calculated for the random forest. Sensitivity tells us that the random forest is slightly better at correctly identifying positives, which, in this case, are patients with heart disease. Specificity tells us that logistic regression is slightly better at correctly identifying negatives, which, in this case, are patients without heart disease. We would choose the logistic regression model if correctly identifying patients without heart disease was more important than correctly identifying patients with heart disease. Alternatively, we would choose the random forest model if correctly identifying patients with heart disease was more important than correctly identifying patients without heart disease. Bam! In the confusion matrix stat quest, we calculated this confusion matrix when we tried to predict someone's favorite movie. Now let's talk about how to calculate sensitivity and specificity when we have a confusion matrix with 3 rows and 3 columns. The big difference when calculating sensitivity and specificity for larger confusion matrices is that there are no single values that work for the entire matrix. Instead, we calculate a different sensitivity and specificity for each category. So for this confusion matrix, we'll need to calculate sensitivity and specificity for the movie Troll 2, for the movie Gore Police, and for the movie Cool as Ice. Let's start by calculating sensitivity for Troll 2. For Troll 2, there were 12 true positives, people that were correctly predicted to love Troll 2 more than Gore Police and Cool as Ice. So for true positives, we'll plug in 12. And there were 112 plus 83, which equals 195 false negatives, people that loved Troll 2 but were predicted to love Gore Police or Cool as Ice. So for false negatives, we'll plug in 195. And when we do the math, we get 0.06. Sensitivity for Troll 2 tells us that only 6% of the people that loved the movie Troll 2 more than Gore Police or Cool as Ice were correctly identified. Now let's calculate the specificity for Troll 2. There were 23 plus 77 plus 92 plus 17 equals 209 true negatives, people that were correctly predicted to like Gore Police or Cool as Ice more than Troll 2. So for true negatives, we'll plug in 209. And there were 102 plus 93 equals 195 false positives, people that loved Gore Police or Cool as Ice the most, but were predicted to love Troll 2. So for false positives, we'll plug in 195. And when we do the math, we get 0.52. Specificity for Troll 2 tells us that 52% of the people who loved Gore Police or Cool as Ice more than Troll 2 were correctly identified. Calculating sensitivity and specificity for Gore police is very similar. Let's start by calculating sensitivity. There are 23 true positives, people that were correctly predicted to love Gore police the most. And 102 plus 92 equals 194 false negatives, people who loved Gore police the most but were predicted to love Troll 2 or Cool as Ice more. When we do the math, we get 0.11. Sensitivity for Gore police tells us that only 11% of the people that loved Gore police were correctly identified. Now let's calculate specificity. There were 12 plus 93 plus 83 plus 17 equals 205 true negatives, people correctly identified as loving Troll 2 or Cool as Ice more than Gore police. And 112 plus 77 equals 189 false positives, people predicted to love Gore police even though they didn't. And when we do the math, we get 0.52. Specificity for Gore police tells us that 52% of the people that loved Troll 2 or Cool as Ice more than Gore police were correctly identified. Lastly, calculating sensitivity and specificity for Cool as Ice follows the same steps. We identify the true positives, the false positives, the true negatives, and the false negatives, and then plug in the numbers. First for sensitivity, then for specificity. Double bam! If we had a confusion matrix with 4 rows and 4 columns, then we would have to calculate sensitivity and specificity for 4 different categories. Little bam! In summary, sensitivity equals the true positives divided by the sum of the true positives and the false negatives. And specificity equals the true negatives divided by the sum of the true negatives and the false positives. We can use sensitivity and specificity to help us decide which machine learning method would be best for our data. If correctly identifying positives is the most important thing to do with the data, we should choose a method with higher sensitivity. If correctly identifying negatives is more important, then we should put more emphasis on specificity.
이번 참조 동영상에서는 바이어스와 베리언스의 차이에 대해서 배웠고, 컨퓨전 매트릭스, 그리고 센서티비티와 스페시피시티에 대해서 배웠습니다. 이들은 임밸런스 클래스 프로블럼과 관련이 있습니다. 많은 클래시피케이션 문제들은 클래스가 스큐되어 있습니다. 즉, 하나의 클래스가 다른 클래스보다 훨씬 많은 레코드 숫자를 갖고 있습니다. 예를 들면 크레딧 카드 프로드 경우에 정상적 트랜잭션이 사기인 경우보다 훨씬 레코드 숫자가 많습니다. 인트루전 디텍션도 마찬가지입니다. 디펙티브 프로덕이 매니팩처링 어셈블리 라인에서 100만 개당 몇 개밖에 안 될 수 있습니다. 이러한 임밸런스 클래스에서 챌린지는 애큐러시와 같은 이밸루에이션 메저가 임밸런스 클래스에는 적합하지 않다는 것입니다. 리얼 클래스를 발견하는 것은 건처 더미에서 바늘을 찾는 것만큼 어렵습니다. 이러한 문제를 해결하기 위해서 컨퓨전 매트릭스 개념이 도입되었습니다. 행에는 액츄얼 클래스가 있고 열에는 predicted 클래스가 있습니다. A의 경우에는 TP, true positive라고 하고 B는 FN, false negative라고 하고 C는 FP, false positive, D는 TN, true negative라고 합니다. 여기서 actual class에 yes를 positive라고 하고 no를 negative라고 하면 이해하기가 쉽습니다. A의 경우에 positive로 predict해서 positive로 actual class가 나왔기 때문에 true가 됩니다. D의 경우에는 네거티브로 프리딕트해서 네거티브로 액츄얼 클래스가 나와서 true가 됩니다. 첫 글자를 따서 A의 경우에는 TP, D의 경우에는 TN이 됩니다. 마찬가지 방식으로 적용하면 B의 경우에 FN, C의 경우에 FP가 됩니다. accuracy는 가장 널리 사용되는 매트릭입니다. A와 D를 더한 것에 A, B, C, D 모두 더한 것을 나눈 것입니다. 이 매트릭은 임밸런스 클래스에서 D 값이 커짐에 따라서 점점 효용 가치가 떨어질 수 있습니다. 사례를 통해서 accuracy 척도의 문제점을 살펴보도록 하겠습니다. 바이너리 클래스의 경우에 만일에 클래스 no의 사례가 990개가 있고 클래스 yes의 사례가 10개가 있다고 하겠습니다. 만약 모델이 모든 것을 클래스 no로 예측한다면 사실상 고장이 난 것과 다름이 없는데 이때도 accuracy는 990 나누기 1000이 돼서 99%의 확률로 정확한 것이 됩니다. 이것은 misleading합니다. 왜냐하면 모델은 yes 사례를 전혀 디텍트할 수가 없기 때문입니다. 이러한 real 클래스를 디텍트하는 것이 사실 더 중요할 수 있습니다. 예를 들면 fraud, 사기나 intrusion, 침입이나 defect, 불량품들을 발견할 때에는 하나의 클래스가, 즉 yes 클래스가 소수이지만 훨씬 더 중요합니다. 이러한 imbalanced 클래스 문제를 해결하기 위해서 다른 척도들이 제안되었습니다. precision P는 A를 A 더하기 C로 나눈 것입니다. recall R은 sensitivity라고도 하는데 A를 A 더하기 B로 나눈 것입니다. F measure F는 위에서 정의한 P와 R을 이용해서 이 RP를 R 더하기 P로 나눈 것인데 이는 EA를 EA 더하기 B 더하기 C로 나눈 것입니다. 이 메저들의 공통점은 accuracy와 다르게 식에서 D를 제거함으로써 임밸런스 클래스 문제를 해결하려고 한 것입니다. 다음은 measure를 계산한 사례입니다. precision P는 10 나누기 10 더하기 10이 돼서 0.5입니다. recall R은 10 나누기 10 더하기 0이 돼서 1이 됩니다. F measure F는 2 곱하기 1 곱하기 0.5에다가 1 더하기 0.5를 나누어서 0.62가 됩니다. 반면에 accuracy는 990 나누기 1000이 돼서 0.99가 됩니다. 이처럼 임밸런스된 클래스에서는 precision과 accuracy 간에 큰 차이가 날 수 있습니다. 두 번째 사례에서 precision P는 1 나누기 1 더하기 0이 돼서 1이 됩니다. recall R은 1 나누기 1 더하기 9가 돼서 0.1이 됩니다. F measure F는 0.18이 됩니다. accuracy는 991 나누기 1000이 돼서 0.91이 됩니다. 이 경우 precision과 accuracy는 모두 높은 값을 가집니다. 문제는 recall 값이 너무 낮은 데 있습니다. 이것은 클래스 no로 예측한 것이 실제로는 yes인 사례가 9건이나 되기 때문입니다. 이처럼 서로 다른 메저들은 모델의 특성을 파악하는데 유용하게 활용될 수 있습니다. 클래시피케이션 퍼포먼스의 메저를 요약한 것입니다. accuracy는 positive 클래스와 negative 클래스를 동등하게 취급합니다. error rate는 1 빼기 accuracy입니다. precision은 imbalance 클래스 문제를 해결하기 위해서 고안된 것인데 positive predictive value를 중심으로 합니다. TP 나누기 TP 더하기 FP가 됩니다. recall은 sensitivity, TP rate이라고도 하는데 TP 나누기 TP 더하기 FN입니다. specificity는 precision과 정반대로 tn rate를 중심으로 한 것입니다. tn을 tn 더하기 fp로 나눈 것입니다. fp rate는 알파라고도 하는데 1 빼기 specificity입니다. fn rate는 베타라고도 하는데 1 빼기 sensitivity입니다. 파워는 sensitivity라고 하는데 1 빼기 베타입니다. 주의할 점은 이러한 용어들이 classification performance라는 도메인 안에서만 사용된다는 점입니다. 다른 도메인으로 가게 되면 여기 나온 용어들이 다른 의미로 사용될 수 있으니 유의하시기 바랍니다.